Yes, four contact sensors are indeed very simple devices, potentially simple devices that can be excellently integrated into CMOS technology, and therefore they lend themselves for realizing complex systems. So I will first talk about four contact devices in general, a little bit of theory, before moving on to some of the implications, namely that we can measure out-of-plane sensors, physical out-of-plane, so we can measure in-plane magnetic fields, and we can do likewise with mechanical stress sensors. These are novel devices that go beyond state of the art, and at the end I will conclude. So let's start a little bit with theory. Everyone knows about four contact sensors. Here is a simple resistor with four contacts. A current is sent across from contact 1 to 2, and the voltage difference is measured. The voltage drop is measured between contact 3 and 4 as the output signal. Everyone knows that these are excellent temperature and stress sensors. Also known are Wheatstone bridges, where four of these resistors are combined into one device, and again a current can be sent diagonally across such a device while a voltage difference is measured between two nodes perpendicular to the current direction. And again, it is well known that these devices are excellent stress sensors. However, driven in this mode, they are also temperature sensors because of the resistive changes of the thermal resistance changes. However, if you operate them as at fixed voltage, then this temperature dependence is somehow weakened to the dependence of the piezoresistive coefficients on temperature. And finally, a third device that is also generally known is the Hall sensor, a four-contact device that usually has its conductive area filled with four contacts. Again, a current is sent across the device while the Hall voltage is measured across. So these are definitely magnetic field sensors, but they're also stress sensors, and of course, why should they be also temperature sensors at the same time? So some of the questions we may ask ourselves here is, what is the influence of the geometry on those respective sensitivities? Why is that a good magnetic field sensor and not the Wheatstone bridge? And why is the Wheatstone bridge a better stress sensor than, for instance, the Hall device? And certainly, well. And so to summarize those considerations, it is clear that these sensors are temperature, stress, and magnetic field sensors to some extent, and the response depends, of course, on material transport properties like the resistivity, the Hall mobility, piezoresistive coefficients, and then they will certainly depend on doping levels N and P. The geometry has its word to play, whether it's a 1D resistor or a 2D device like the Hall sensor, or maybe a 3D device, why not, to get out some response. And the shape in these dimensions is certainly determinant for giving you a certain response. And also these devices can be operated in different modes. You can operate them as voltage or current biasing. You can also think of rotating currents through them by using different pairs of contacts to drive them. And then the question about technology, what to use, field effect transistors, the inversion layer of field effect transistors, or currents in diffuse structures could be applied. And then since these are technical structures, they are non-ideal. And then the question can be raised how to compensate some of those non-idealities. So to start with the theory, let's look at a very general four-contact device, arbitrarily shaped, obviously, with two contacts being used for driving the device and another contact pair for recording a voltage drop. And this device may be exposed to a magnetic field and a mechanical stress at the same time. And if you want to replace it by a simple schematic, well, here would be the four-contact device, and then we would have the direction of the current and the voltage recording procedure in orthogonal directions. Now, you can also exchange these instrumentations, making the voltage measuring contacts the drive contacts and vice versa. And in the two-dimensional picture, that would just correspond to a rotation of the instrumentation around the device, 90-degree rotation, an orthogonal rotation. And we call these two operation modes A and B, and this will be of significance later. So let's consider some of the intrinsic transport phenomena. Of course, the current density in these devices is related to the field vector by some electrical conductivity matrix, sigma electric. That in turn depends on the mechanical stress and the magnetic field. And there is a very profound theorem due to Onsager that says that this matrix has a very particular property. It's symmetric. Well, it's almost symmetric because if you take the transpose T of sigma, then you have at the same time to inverse the magnetic field. This is due to some profound physical principles, microscopic reversibility, and it's one of the consequences of irreversible thermodynamics on which Onsager worked. So in the case of a conductivity in the absence of magnetic field and mechanical stress, it's a very simple matrix. It's just a diagonal matrix in an isotropic material. Now, again, a simplified case with one scalar parameter, and surely this matrix is symmetric as Onsager has predicted, no doubt about that. If we turn on a magnetic field, then we get some additional elements in the off-diagonal elements, and these are now anti-symmetric exactly as Onsager says. If you mirror the matrix with respect to its diagonal, if you transpose it, then you have to add minus, and then you recuperate the same matrix as before. If you add mechanical stress instead of magnetic field, then these additional elements that come on top of the ones and the zeros of before, well, these elements are symmetric pairwise, and so mechanical stress implements a change of the conductivity matrix that's symmetric with respect to the diagonal. And this antisymmetry and symmetry has profound consequences on the response of these devices. So let's look at that in detail. You see here the two measurement configurations A and B, and let's assume we send in a current equal to 1. There will be a current distribution through the device that we denote IA, and in the other case we denoted IB. These are current distributions, although they are represented here by vector, simple vectors, but they are really distributing through the device, and so therefore we have this vector of R. And what can you do with two vectors? You can do a cross product, and you can do a scalar product. Why to do that? Well, let's keep that in mind when we calculate the response of such a device to a magnetic field. The device response will be some offset voltage. In the absence of a magnetic field, we will measure some voltage drop across the device, and so there will be some voltage which we can represent as I times R, an offset R times I. And then if we turn on the magnetic field, there will be an additional contribution that is proportional to B in the linear approximation, and that proportionality is given by a sensitivity vector scalar product with B, and then of course the response will be proportional to the current that is sent through the device. And when we now calculate explicitly these sensitivity components and this offset resistance, well, amazingly, that cross product and the scalar product just have to be integrated over the space of the device. You have to integrate those with the Hall mobility and the resistivity tensor in the absence of a magnetic field, and you obtain the sensitivity of the Hall device and the R offset. And that would be expression in the case of the measurement configuration A. That's an amazing result. It's valid for an arbitrary shape. It's a very simple expression that allows you to compute S and R, and you don't even have to solve any problem in the presence of a magnetic field. You can rely on the magnetic field-free solutions of the Laplace equation. It's a very simple problem, as you know. Now, in case B, we rotate the currents by 90 degrees, so there are some exchanges, and the consequence of that is that the sensitivities of those two cases A and B are mathematically identically. Although we are having totally different experimental situations, obviously. But the sensitivities are identical, and the offset voltages are opposite. So that's a good feature to have, because if we take the two operation modes and take the output voltage of both cases and average over them, because of this minus sign, we can exactly remove the offset. And the remaining signal is a signal that goes linearly with B without offset, a property that you would expect of any good sensor. So we have here an excellent way of making excellent Hall sensors out of such an arbitrary shaped device. That's a surprising result. If you take the difference of the output voltages, you identically eliminate the magnetic field sensitivity. So the resulting sensor has no sensitivity at all on the magnetic field. However, it still has an offset, and that offset now is composed of two terms, a response to the mechanical stress acting on the device, and then some residual offset that is due to the geometrical shape of the device. Even in the absence of magnetic field and mechanical stress, you will have some offset voltage, some voltage drop over these devices. So again, you have a linear sensor for stress. So to conclude that part, let's see. Of course, we have learned about the hidden symmetries of such arbitrary shaped devices. We call that reciprocity. We have seen that the sensitivity of out-of-plane components of B needs a cross product that must be out of plane, and therefore the current flows to measure an out-of-plane component BZ needs to be in the plane, and that leads to the usual design of planar Hall sensors, Hall plates, as we have used them for ages. If we want to have in-plane sensitivity for components in the plane of the chip, then of course the cross product must be in the plane, and therefore at least one component must be perpendicular to the plane, one current component. So that leads to a design of sensors where a current can flow into the chip and not just in the plane of the chip. And then we may hope to have sensors sensitive to Bx, By, and well, in the case of the mechanical sensors, to be sensitive to components that the planar sensors are not sensitive to. This is the sensitive component, stress component of the planar sensors. And then we have also seen that the residual offset, well, is unavoidable unless we design symmetric structures. Then the measuring contacts are on equipotential lines, and then their voltage difference is zero. And of course, also a consequence that I have not demonstrated is that resistors are really bad magnetic sensors. Actually, their response goes like B square, and there is no way to squeeze out a linear response of B out of them. So how should we design optimal Hall plates? Well, if we want to optimize the sensitivity with respect to a given current, that is the output voltage per magnetic field per current, then the long resistor with perpendicular contacts is the best device. And any device that can be obtained from that by a conformal mapping, turning it into an equivalent other object with exactly the same electrical properties, will have the same sensitivity, and that sensitivity is just the Hall mobility times the sheet resistance, or expressed differently, the usual sensitivity that you know from the textbooks. So what is an equivalent shape? For instance, this circular shaped Hall plate with 4 contacts, point shaped contacts, is excellent, and you will have exactly that optimal sensitivity. Now, if we go to asking the question, how should a device look like that is optimized with respect to a given drive voltage? Well, V out per D per B per input voltage, then the optimal device has a simple shape. Again, it's a circle with contacts that span 45 degrees. So the insulating region is 45 degrees and the contacted region as well. And this device has the optimum sensitivity for such a symmetric device with 0.47 μh, which in case of N-silicon amounts to about 6.8% per Tesla, which means that if you apply 1 Tesla to a device and 1 volt, you will get 68 millivolt out. And of course, any device that is equivalent in shape, of electrically equivalent of different shape obtained by conformal mapping will have the same properties, exactly the same properties. Now, what is the real optimum? We might ask. Well, that's a device like that that has point-like contacts in small gaps between large contacts, and that will have a slightly higher sensitivity, 11% per Tesla. But of course, you must recognize that a large current is going to flow here, and so from the energy consumption point of view, that's not a good device. The previous device is definitely better. So in the case of piezoresistive sensors, what is the best device there? Well, actually, it's the traditional Wheatstone bridge. And there we can ask the question about the sensitivity with respect to a particular stress component, sigma ij, with respect to the input voltage. And if you draw the Wheatstone bridge in this arrangement, referring to this coordinate axis parallel to the wafer flat, well, then this device is going to be excellently suited for measuring sigma xx minus sigma yy. And the sensitivity is going to be pi 44 half. And of course, you know that pi 44, this piezoresistive coefficient, is particularly high in P silicon. 69% per gigapascal is what you get out. If we turn the device by 45 degrees, well, then it's good for measuring sigma xy, and you have this sensitivity pi 11 minus pi 12, which is high in N silicon, and therefore the resistors is going to be N silicon, and you get minus 156% per gigapascal. So significant responses, even at the 100 or 10 or 1 megapascal level of stresses. Now, I would like to move on to the magnetic field sensors, and consider out-of-plane sensors in particular. So here is an example of an N-well, a deep N-well, maybe 10 micron deep, not so wide, which has 5 contacts here. And you may ask, why 5 contacts? Well, actually, we are connecting the outer 2 contacts, so that makes contact 1, common contact 1, and then we have 2, 3, and 4. And we can bias these devices with a current that now goes into the device, not a planar device. It goes into the silicon and out again, and so we can hope to have a sensitivity to an in-plane component of the magnetic field. These show photographs of realized devices and a schematic indicating some dimensions. So if we derive the device now in this way, of course, the magnetic field will influence the current distribution here and create a voltage output across those devices. However, the response is weaker than in the ideal device. It doesn't look at all like this optimally shaped device, and that's why you only get 2% per Tesla out of such a device. Even worse, the offset is large, 15 millivolts typically at 5 milliamps of driving current, and that's really worrisome because this voltage is much larger than what you can hope to get out as a magnetic response from the device. So we really have reason to compensate for that offset and ask ourselves the question, why is it in the first place so high? So to study that question, we can operate the device in several modes. So we can send the current like this or in the opposite direction, and then increase the current that flows through the device. And as a function of the input voltage, we see that actually the offset voltage increases very largely and reaches 10 millivolts roughly here in this case. And you also see that this is roughly linear, with a small quadratic contribution. If we now exchange the currents in this orthogonal switching logic, well, then the current will flow through contact 2 to contact 4, and then voltages are measured between 1 and 3. And, well, here the situation is even worse. You get very large offset voltages. However, if you take the average of these 2 red curves, you get something which is very similar to what we had in black before, but just with the opposite sign. So it looks like these red curves are the black curves with reverse sign plus an additional quadratic component in the positive and negative direction. Now that's a bit too systematic to be arbitrary, and therefore we have reason to study some physics here. And well, you see that there is systematics behind also by the fact that if you add up these components, well, the sum is just close to 0. Actually, it's still 50 microvolts or something like that, which is still large in comparison with the magnetic field signal. So we have still, even after compensation of this offset by switching, by adding up these signals, we still have reason to understand it and to hope to improve it even further. So to understand that offset, we can look at the device in a simple way. We have these 5 contacts that separate the conductive N-well into 4 segments, 4 resistor segments that are schematically shown here. The inner segments have resistance Ri, the outer ones Ro. And, well, for generality, we have to distinguish these resistances because the geometry of this resistance is different from the geometry here. This one is terminated, whereas this is not terminated at the same location. So we have these 2 resistance values. And then, of course, we are shunting the outer resistance by a non-ideal resistor. And we can identify 4 contacts. And then we can pull on those contacts to deform the structure. And then it's amazingly just a Wheatstone bridge. And that Wheatstone bridge is very simple to analyze, except for the fact that these resistors that you have here are not just resistors, they're more complicated. Well, first of all, they're not just R0 or RO, they're slightly different. Each of them is slightly different because of technological reasons. So there is resistive mismatch that we have to consider. And then these are semiconductor resistors. So they have a PN junction that is modulated by the application of the potentials that you apply to the resistor contacts. And therefore, we have a nonlinearity. The resistance are voltage controlled. Yeah? And now the resistive bridge becomes a little bit more complex. Yet you can analyze it and amazingly model the response quite well. You have this roughly linear response of the modes 1 and 2, and the linear plus quadratic modes here, modes 3 and 4. And the average of those two is indeed roughly opposite to the blue curves, and the total average is relatively flat. And you obtain that modeling result with very reasonable assumptions. So the inner and outer resistors are almost equal. Yeah, they're not equal, but they are very close to each other. The alphas, the resistive mismatch is 1/10% in these resistors. That's not very much, and that's what you have to expect from technological reasons. And then these beta coefficients, the junction field effect coefficients that turn these resistors into nonlinear resistors, well, they're almost the same for the outer and inner resistors, but not exactly the same. And these are the reason for these offset values. So in order to make these vertical Hall sensors perfect, what would you have to do? You would have to have sensors with Ri equals R0 and the same beta coefficients. You would have to have an ideal shunt resistor, and you should have no resistive mismatch among the 4 segments. That would be perfect. Yeah? And so this geometry as a conclusion should be as symmetrically as possible, and then you would have no linear nor quadratic offset, and you would be one level higher. Yeah? We have an implementation of that device that I cannot present you yet because it is still in the phase of patenting, but that can be turned into a very neat idea that I hope to present at a future conference soon. So let's consider mechanical stress sensors with out-of-plane components. So here is a device that has, again, 4 contacts. 1, 2, 3, 4. And this one, again, is the same here. So it looks very similar to the previous contact. You have an end well surrounding this central channel, and current is injected from the center down up to the collector contact up here. And so what you also see is equipotential lines under an applied mechanical stress, that is an out-of-plane mechanical stress, and you see that these 2 measurement contacts have different potentials. So you measure a signal V out that is proportional to the mechanical stress, sigma YZ in this case, and of course proportional to the input voltage, the drive voltage. And then there is a piezoresistive coefficient, and there is a geometry factor, which takes into account that this device, again, is not an optimal Wheatstone bridge. Yeah? So if you drive that device at V in, it's temperature compensated. That is, that thermal resistance changes are no longer important, but of course the pi coefficient is still temperature dependent. So you also see that we have an additional pair of contacts here in the orthogonal direction viewed from top, and that's just easy to make a sensor that is sensitive to both out-of-plane shear stress components in one single device that has a size of about 50 by 50 micrometer square. And the device works really nicely. We apply shear stress in one direction, positive and negative. You get a nicely linear response with signals that are appreciable in the range of millivolts if driven at a few volts. And such a device has little cross sensitivity to other stress components, as is expected of a good stress sensor. There is a second device able to measure an out-of-plane stress component. A resistor-based device. You see here vertical resistors connected to a horizontal resistor. Again, current is injected into the depth of the end well and extracted here through these vertical paths. And so we have a resistor composed of these 3 components, and we can define a geometry factor that says the fraction of the resistance that is actually contributed by the vertical parts. So this must vary from 0 to 1. And then the piezoresistive signal of that resistor will change depending on mechanical stress components and on temperature. And what we have here are transport properties and then this geometry factor. So you're able to at least be sensitive to sigma ZZ with this device. And one advantage of the device is that you can modulate its geometry by suitable operation. You have this depletion layer surrounding the P-well. By applying a voltage to the P-well with respect to the N-well, different voltages, you can expand or contract that depletion layer, and therefore you can make the channels smaller and this changes the geometry factor. Yeah? So you can operate the device in two different geometry factors, and that means that you can use two measurements to combine relative resistance changes in two operating modes with each other into an output, yeah, using the gamma 1s and gamma 2 of these two measurement configurations to get out a piece of information you didn't have without the device, namely a combination of stress information that also implements sigma zz, the out of plane normal stress. Yeah, again, this device can be tested. Here it's an array of such devices, 5 by 5 array, and we have grown a nickel bump on top of the array, and we are pressing with a device on top of that nickel bump, and then you can measure the stress distribution of the caused by that external force of 1 Newton. So what to do in terms of application with these sensors? Here is a CMOS chip fabricated at X-FAB in 0.6 micron CMOS technology. It contains lots of sensors. These are the colorful squares that implement planar sensors of the piezo-fed types we have reported many times before, but also the out-of-plane shear stress sensors in appropriate locations. And of course, there's digital logic to drive the signal. There's an I2C bus, and there's some analog logic to amplify the signal. And well, that structure is used in what we call the smart bracket. So these are brackets, as you know them from orthodontic treatments, but each bracket has one of those chips sandwiched in between the base and the slot region. So when a force is applied to any of those brackets, a vectorial force and a vectorial torque, you can of course measure the stress caused by that external constraint in the sensor chip, at the various locations of the sensors, the various components of the stress, and from that total amount of information you can extract which force and torque is being applied to each individual tooth in such a dentition. Now, of course, that's an artificial dentition used by our orthodontist colleagues, and a fully instrumented typodont that allows them to optimize their therapies. And of course, in the long run, we may think of implementing these things in real patients, but a few technological and biocompatibility questions have to be solved before. Here's another example showing a chip of about the same size, 2 by 3 millimeters, with an array of sensors, actually an array of cells that each of which contains a lot of individual sensors. So you have planar sensors for measuring these components. We have the vertical resistance sensors and the vertical shear sensor that I described before, in addition to a PTAT sensor, and that's repeated 10 by 10 times. It's a chip used for packaging characterization. And the next chip is exactly also used for packaging characterization in the labs of one of our the industrial partner. It's a large chip, 8 by 3 millimeter squared. It's for testing flip chip interconnects in this array of over 700 flip chip pads that have bumps grown on them, and it's full of sensors beneath. You cannot really see them, but anyway, 19 contact pads are used to power the device. There's ESD protection. There is digital logic with an 11-bit multiplexer to contact the overall 1250 stress sensors that are distributed under these different bumps, and you can extract all the information within 20 seconds. And then we have, in certain locations, we have high resolution arrays under bumps, so it's kind of hard to see, and that's why I would like to show one example here. A stress sensor array of 5 by 5 with its logic around its transmission gate, and then the array is 150 by 150 micrometer square. This would be the size of a bump, and you can of course record the stress exerted by the packaging on those bumps in the various locations here in the corners, in the middle of the sides, and somewhere more centrally on the chip, and therefore provide valuable information to the microelectronics company active in this region. And so here is an artist's view of one of those stress sensor arrays in the corner, and a recorded stress distribution caused by its delicate location in the corner of the chip, which is always the toughest point for these packaged chips. So with this, I would like to conclude. I have shown you that we have explored 4-point sensors theoretically. We have learned about reciprocity and hidden symmetries in these devices. We have investigated vertical Hall sensors. I have named some of their non-idealities and how to deal with them. And finally, we have applied these novel vertical stress sensors in new contexts, particularly the smart bracket and packaging characterization applications. Thank you for your attention.